loading. Okay, so let's get started. So I announced the midterm week to be next week, so starting this Friday. So that is basically going to be just a big homework you're supposed to do your own. It's take home, open book, but no help from humans. So I just uploaded a pledge form you are supposed to sign and upload by this Friday. And that it counts for 10 points out of the 200 points of the midterm. So you don't want to miss it. So just read and sign, upload it by this Friday, okay? All right, so we started talking about fermions. So the first thing we did is to change the commutation relations among the creation and annihilation operators to anti-commutation relations to make sure that we can occupy a given state only once for fermions, and that's the requirement for fermions, obviously. And we will see how that actually leads to an anti-symmetric wave function as we actually go on today. So the idea is that once you have these anti-commutation relations, so AB anti-commutator is AB plus BA, not AB minus BA. And then if you actually write this out, then you can start talking about the Hilbert space that where the creation and annihilation operators acts on. So just like in the case of the usual harmonic oscillator, we prepare the vacuum state by this definition that it is a state annihilated by the annihilation operator I'm calling B to distinguish that from A. And then you can create an excited state, which is a number state with number 1, by acting the creation operator on this vacuum state. So far, everything is exactly the same as you have been doing with a regular harmonic oscillator. But now comes the difference. So this state 1 cannot be raised any further. So if you act B dagger creation operator on this state 1, state 1, by definition, is the state where creation operator acts on the vacuum state. So now writing it out, I have 2 powers of the creation operator, which is the same thing as the anti-commutator between 2 creation operators, except for a factor of half, right? So this is anti-commutator, so this is B dagger, plus B dagger in the opposite order, but they're the same operator, so it's just twice B dagger. And so if you put a half on it, and that's the same thing as B dagger. But what we did here in this anti-commutation relations is that B dagger anti-commutator vanishes. So this vanishes. So if you look at the beginning and end, acting B dagger on 1 returns 0, which means that singly occupied state cannot be raised any further. You cannot put 2 particles into the state, and that's exactly what we want for fermions. So that's how anti-commutation relation really helps us to deal with the fermions. So as a result, for a single harmonic oscillator, which I call fermionic harmonic oscillator, the Hilbert space has only 2 states: the vacuum state, number state with number 1, but nothing else, and that's it. So your Hilbert space is only finite dimensional, consisting of only 2 states, whether it is occupied or not occupied, and that's it. So that's exactly what we need for fermions. Okay, so let me pause here. Are there any questions about this? And obviously, right now, I'm just doing a single harmonic oscillator, and we have to promote this field, just like what we have done with the bosonic harmonic oscillator. So this B ends up being an annihilation operator, which is a field as a function of space. So that's the next step we have to go through. All right, any questions about this? Go ahead.
Yeah, I have a question. So how would we take spin into account?
That's a very good question. And what you have to do then is to introduce 2 sets of creation annihilation operators for electron, so that you have BB dagger for spin down state and BB dagger for spin up state. Then, because you have two sets of these fermionic harmonic oscillators, then the Hilbert space now 2 to the 2, 4 states, namely that vacuum state, singly occupied by spin up, singly occupied by spin down, and doubly occupied by one spin up and one spin down electron, but you cannot raise any further. So that's just have two copies of this two-dimensional Hilbert space with the two copies of this anti-commutation relations. Does that answer your question, Chirag?
Yeah.
Okay, Adi?
Yeah, I have a quick follow-up to that. So does that kind of correspond to the product state of spins that we talked about? And then is there like a annihilation creation for the total spin eigenstates?
Annihilation equation, total spin eigenstates. Yeah. So if you put two electrons in there, so B dagger up and B dagger down, and that is always in the combination total spin 0, because you have spin up and down. And as we will discuss in a moment, it's automatically anti-symmetric. So up down minus down up is a combination that gives you total spin 0, right?
Okay, right. So you just do the same transformation that you would do before. You don't have to do anything else. Like Klepp's coordinate stuff still works.
Right. So if you go to much sort of a more general problem, that B can also be in position space, that you can talk about creation annihilation operator at each position. Or you can go to momentum space, then you can talk about creation annihilation operators of electron in a given momentum. And then you introduce two sets for spin up and spin down for each momentum or each position. And that's how we actually end up in QFT instead of just a quantum mechanics of this weird harmonic oscillator. Okay, any further questions? All right, so let me move on. So there's one thing which is really funny about this fermionic harmonic oscillator. So if you go back to the discussion we had a long time ago about the usual harmonic oscillator, so we started the harmonic oscillator from the usual Lagrangian of half mx dot squared minus half m omega squared x squared. We introduced the creation annihilation operators, and then we rewrote Lagrangian using creation annihilation operators. So that's something you have done in your homework problem. And from here, you can see these canonical commutation relations between A and A dagger. So one thing we did is to think about the classical limit of this theory. So in order to avoid any H bar in the Lagrangian, you can scale A and A dagger to absorb H bar to 1/2 power into this definition. Then Lagrangian doesn't have any H bar in it. So then it makes sense to regard this as a classical Lagrangian. And from this classical Lagrangian, if you want to quantize it, then A is the variable. A dagger is the canonical conjugate observable. So A dagger canonical commutation relation would be like this. So that's what you normally do with X and P. So I'm regarding basically A as X, IA dagger as P. So XP is IH bar. I cancel the I from both sides. So that's how we end up with AA dagger equals H bar. And that's consistent with the way it started before absorbing this power of H bar 1/2, right? But now with this way of writing it, with this normalization, we can consistently take the classical limit where H bar goes to 0. So in this limit, all the commutators vanish. And that's something, well, we know, namely that when you go to classical mechanics, all of these observables commute because they are no longer operators. So they become just pure numbers, and that's something we know very well from classical mechanics. So as expected, once you take a consistent classical limit, then everything commutes because there's no concept of operators. Everything becomes just numbers. So that's something we are very familiar with and from quantum mechanics class. So the question is, what happens if we do the same thing for this fermionic harmonic oscillator? And that is the next slide. But again, let me stop here to see if there are any questions about this classical limit. No? Yeah, I think this is fairly obvious and clear. So now I try to apply the same argument for this fermionic harmonic oscillator. So now I have this B thing instead of A. And they satisfy this canonical anti-commutation relations. So the way we did it, in the same way we did on the previous slide, now I absorb a power of h bar to 1/2 into the definition of B and B dagger, so that Lagrangian becomes free of h bar. So now Lagrangian looks classical. And the canonical anti-commutation relation, of course, comes from regarding B as a variable, IB dagger as its canonical conjugate. And then, so this is the anti-commutation relation. And now we can safely take the limit of h bar going to 0. Then all of these anti-commutators vanish, which sort of looks fine at the casual look. But if you think a little bit more deeply about this, this is actually very strange. Everything anti-commutes in classical physics. And in particular, B squared is a half of BB anti-commutator, so that vanishes. B dagger squared is a half of this anti-commutator, that also vanishes. And BB dagger anti-commutes without h bar here, so BB dagger is negative B dagger B. When you interchange the order of things, you get minus sign. And this is the kind of number you have not seen before, I believe. But mathematically, you can define such numbers, and they are called Grassmann numbers, or to be more precise, Grassmann odd numbers, because you can refer to the ordinary numbers as Grassmann even instead. So we are talking about these weird numbers now, which anti-commute. They are no longer operators because we have taken classical limit, but nonetheless, they anti-commute. And from the point of view of algebra or ring in mathematical terms, you can define the multiplications of various quantities, and you can impose various relations on those multiplication rules. And here we're imposing this multiplication rule that the product of two objects, A times B, is the same thing as B times A up to minus sign. Whenever you interchange the order of these things, you always get a minus sign. And that turns out to be the classical limit of this fermionic harmonic oscillator. Sounds really crazy, but that's something we have to accept. And from the point of view of mathematics, there's nothing wrong with it. So we have to sort of just swallow this weird concept of anti-commuting classical numbers in order to understand fermions. So this is getting very bizarre. I try to sort of minimize the bizarreness on the next slide as much as I can. But let me stop here again. I'm sure you got some questions.
I have a question.
Right, Riley.
Do you know an example of Grassmann odd number, just like off the top of your head?
Yeah, so one thing you might know, actually something you do know, is the cross product in vector calculus. So if you have vector x and you have vector y, you can define x cross y. And if you interchange the order, y cross x is the same as negative x cross y. So that's another example of anti-commuting objects. And a more general version of this is called differential forms in differential geometry. So in any dimensions, you can define what is called differential forms, and they anti-commute by this multiplication rule called wedge product. So you do have a system where every multiplication is actually anti-commute. So the cross product in vector calculus is probably the closest thing that comes to this idea of anti-commuting objects. Does that answer your question, Riley?
Yeah, it does. Thank you.
Okay. Any other questions? Okay. Just to minimize this bizarreness as much as I can, let me just remind you, when you first learned about the imaginary number, I being square root of -1, I don't know if that was a middle school or high school, but I'm sure you felt like, okay, this is just a pure academic mathematical artifacts. It's the name indeed says imaginary, so it can't be anything real about this. So this is just introduced for the convenience of some mathematicians' desire to be complete, that you can always solve the second order polynomial equation. And if you define this, you can always find two solutions. So that is fine. But you probably thought that, okay, this was never really real in any sense. Has nothing to do with the real world. But now that you have studied quantum mechanics, you are using I every day, right? Because when you write a Schrödinger equation, you need I in it. So all of a sudden, complex number became part of your daily life. So whenever you think about quantum mechanics, you cannot avoid imaginary numbers or complex numbers. So something you might have thought to be purely mathematical artifact is something you need in order to describe what you actually measure in your laboratory. And I'm sure by now you have gotten used to this idea. We use these imaginary numbers or complex numbers in general to describe physics, which has to do with the real world. But if you think back at the days when you first studied this, I'm sure you didn't expect that. So sometimes you learn about new mathematics where you get exposed to something really bizarre. You might not think that has to do with the real world because it's such a bizarre number, like square of that becomes negative. But at the end of the day, we actually use it. So in the same way, the Grassmann odd numbers, because they are at least mathematically consistent, has a place in real physics, description of the real world. And Mother Nature somehow likes to use these bizarre numbers like imaginary numbers and now Grassmann odd numbers for the purpose of really describing everyday physics around us. And you don't live without electrons in your body. They are fermions. They occupy Pauli exclusion principle, or as I claimed, it better be called a diversity principle. And because of that property, your atom doesn't crash, right? So electrons have the stable orbitals because of that. So you do need these fermions for your life. And in order to describe your life, you actually need these bizarre anti-commuting numbers. You've been there before. Now that's the next step. You accept that imaginary number, looks very bizarre, but now you use it. Now you have to accept a new bizarre number, which is this anti-commuting Grassmann odd numbers. So as long as they are mathematically consistent, somehow Mother Nature has this habit of using bizarre mathematics to describe herself. And this is just yet another example of this. So I hope that makes sense. And I always feel a little funny whenever I talk about the fact of I, because I in the Japanese language is written like this, which means love. So quantum mechanics is actually full of love. Now we are jumping into this yet another step of these Grassmann odd numbers, but we've been there before. So that's the way I try to sort of minimize the shock of seeing these new kind of numbers. And so I hope that's okay. All right, any questions about this? All right. So now we have to think about the quantum field theory. So whenever we actually looked at this Schrödinger field theory, this psi had a meaning of annihilation operator at position x, psi dagger had a meaning of creation operator at position x, and psi dagger satisfy commutation relation of a harmonic oscillator at every position. And so that's how we introduce this whole idea of quantum field theory. But before you actually go ahead and quantize this Lagrangian of the Schrödinger field theory, you have to decide whether this psi is a normal number, Grassmann even, or this bizarre anti-commuting number, Grassmann odd. So when you're just staring at this form of the Lagrangian, you don't know necessarily whether psi is Grassmann even or Grassmann odd. So in order to understand your quantum field theory, not just that you write down this Lagrangian, but you have to specify whether the field is Grassmann even number or Grassmann odd number. So you have two versions of the Schrödinger field theory now. And when you start your Lagrangian written with the Grassmann even numbers, that's the usual numbers, then you quantize it using the canonical commutation relation. And psi-dagger commutator has this usual commutation relation between annihilation creation operator, except that this is now a delta function because this lives in a continuous space. But that's it. So that's something we have done all along over the past 3 weeks or so. But if you do have a Lagrangian written in terms of these weird Grassmann odd numbers, they are anti-commuting objects to begin with. So when you quantize this, then you are supposed to use this anti-commutation relation instead of commutation relation. So you have two versions of Schrödinger field quantum field theory. One version is Grassmann even. That's something we have done all along, and we have proven to ourselves. And part of the homework problem was a two-body case, that Schrödinger field theory was exactly equivalent to two-body quantum mechanics problem, including all the interactions in it. Now you have this weird Grassmann odd numbers. When you quantize it, we want to know that this is really the same content in terms of physics as the multi-particle quantum mechanics of fermions. And that's something you're going to see in the next couple of slides. So you have two versions of QFT now, one with Grassmann even numbers, one with Grassmann odd numbers. When you quantize it, you use commutation relations for the Grassmann even case, but you use anti-commutation relation for Grassmann odd case. And Grassmann even case, we know, is the same thing as multi-particle quantum mechanics of identical bosons. For this Grassmann odd case, we will see that this is also identical to the multi-particle quantum mechanics of fermions. And at this stage, this is an arbitrary choice, whether you use commuting numbers or anti-commuting numbers. But what we will see later on is that when you actually put quantum field theory together with relativity, it turns out that it's not an arbitrary choice. It turns out that for integer spin particles, like photon has spin 1, you are forced to use Grassmann even numbers and therefore commutation relations, and therefore they have to be bosons. On the other hand, if you use spin half-odd particles, like electron with spin 1/2, it turns out that mathematical consistency requires you have to use Grassmann odd numbers, and therefore they become fermions. And that is something called the spin statistics theorem, namely that integer spin particles have to obey Bose-Einstein statistics, and half-odd spin particles should obey Fermi-Dirac statistics. So at the non-relativistic level, that's an arbitrary choice. You can choose it either way. You can even think about spin 0 fermion if you like. But once you go to relativity, it's no longer an arbitrary choice. You are forced to regard spin integer particles to be bosons, spin half-odd particles to be fermions. That becomes actually a prediction from the consistency of the quantum field theory. So we don't see that right now. I'm just giving you sort of upshot on what's coming later in the second half of this course. So relativity actually gives you extra predictions beyond what we do in quantum field theory, namely spin and statistics are correlated, and there's no exception to the rule once you have relativity. So that's coming later. But at this point, let me emphasize again, this is an arbitrary choice at the level of non-relativistic quantum field theory. And once you have these different sets of operators, some of them commuting, some of them anti-commuting, how do you deal with the product of these operators when you have both sets? And the rule is very simple. If you're talking about the products of Grassmann odd, even operators, you always think about commutators. Even when you think about products of Grassmann even and Grassmann odd, you still talk about the commutators. But when you deal with the product of two Grassmann odd operators, then you talk about anti-commutators. So that's a general rule. So as long as even things are concerned, you always use commutators. The only case you are supposed to use anti-commutators when you're looking at the product of two Grassmann odd operators. So that's a general rule you want to remember. Apart from this, you can deal with commutators and anti-commutators just fine with this general definition. And now we are going to see that these anti-commuting fields really do give us the multi-particle quantum mechanics of identical fermions. So we are getting there very soon. But anyway, let me stop here again to see if there are any questions. There are some chats over there. Do Grassmann even numbers correspond to the symmetric algebra? I'm not sure what is meant by symmetric algebra. Shira, can you tell me?
It's just like you quotient out the anti-symmetric products.
Oh, I see. Yeah. So in a sense that if you have the products, you can arbitrarily interchange them. If that's the definition of symmetric algebra, then yes, Grassmann even numbers do correspond to that.
Okay.
All right. Any further questions?
I have a quick question.
Go ahead.
This goes back to what.
Oh, there you are. Okay.
Yeah. So this is about what Chirag was asking about earlier. He asked about spin, and why is it that now we're considering spin for the case of fermions, but we weren't for bosons in everything we've learned so far?
Yeah, so far we have not talked about spins at all. So the idea is actually the same for bosons and fermions. Let's say you have a photon, and we will talk about that later. Then you have two polarization states of, for example, the one polarization or the other polarization in two planes, or you can talk about the left-handed circular polarization and right-handed circular polarization. So you have two polarization states for the photon. And you will see later on that they correspond to basically two sets of the quantum field theory. So one field for one polarization, another field for the other polarization, and the set of these two fields describe the photon. So in the same way, if you have a spin 1/2 particle, so ultimately we have to take the Fermi statistics for them. So you have one anti-commuting field for spin up, another anti-commuting field for spin down, and the set of these two fields describe the electron as a whole. And the spin is something that becomes a integral part of the quantum field theory, again, once you go to relativity. And then we will talk about the Dirac theory, which describes the spin 1/2 fermions. And again, I emphasize that you are forced to use Fermi statistics to quantize spin 1/2 field. But in addition to statistics, that also leads to yet another prediction, namely that for electron, you are supposed to have antiparticle called positron. And that turns out to be yet another prediction of the relativistic quantum field theory. So altogether, you're talking about 4-component field. You have electron with spin up, electron with spin down, positron with spin up, positron with spin down. So you have 4 components of field called Dirac field for obvious reasons. And so your field becomes 4-dimensional column vector. And we will be talking about later in this class. So the basic idea is that once you have spin degrees of freedom, you introduce the equal number of fields as spin degrees of freedom. And in addition, when you have also antiparticles to it, then you need to introduce fields for the antiparticle states too. So in the case of spin 1/2, you end up talking about 4-component Dirac field at the end of the day. But it's still the same idea. You have separate component of the field for each degree of freedom you have in your system. Does that answer the question, Natalie?
Yeah, part of it. I'm just curious as to why we didn't have to consider spin before.
That's simply because we didn't talk about spin.
Oh, okay. Okay.
And we will talk about spin fairly soon.
Okay. All right. Thank you.
Any other questions?
Yeah, I have a couple questions. So, first, like, is a Fock space a graded vector space, since we can kind of express it as a direct sum of Hilbert spaces?
Right. Yep, it is.
Okay.
So you can view this that's graded, whether based on whether state is fermionic or bosonic. That's one way of grading it. So you can assign sort of plus minus sign to each state. So that's one grading you can do. And of course, we learned that in Fock space, you can grade it by the number of particles in the state. That's another way of grading it. And so either way, it is a graded vector space. Yes. If
Yeah,
you
so
like that
then
kind
my
of language.
yeah, so I guess my second question is, does this like this anti-commutation relationship kind of define a graded Lie algebra on the Fock space, or?
Yeah, so the Lie algebra is basically commutation relations among things like angular momenta, for those of you who have not heard about this before. So the Lie algebra is always about certain symmetries. And when you have infinitesimal symmetries like translation or rotation, you can talk about their commutation relations among momentum operators or angular momentum operators. So that's basically what the Lie algebra is about. It turns out that there's something called super Lie algebra, where these different the generators of the symmetries anti-commute. And they have been also classified in the same way the Lie algebra had been classified. So there's a whole mathematical literature about the super Lie algebras, and they had been all studied. And from the physics point of view, you might have heard of this idea that there's something called supersymmetry that would relate bosonic particles to fermionic particles. And that is a popular idea in particle physics, and that also sometimes appears in condensed matter physics. And so if you have this big symmetry, that's why it's called super, right? So the ordinary symmetry can relate only bosons to bosons, fermions to fermions. But if you have this super powerful symmetry that can relate bosons to fermions, that's what we call supersymmetry. And supersymmetry gives you a conserved charge, like any symmetry, according to Noether's theorem. And those charges are actually anti-commuting. And that's one example of the super algebra. Okay? And again, if you don't care about this stuff, don't worry about it. Righty, you have a question too? You're unmuted. Okay, all right. Any further questions? Good. Then now we would like to make sure that this weird field, which anti-commutes with itself, really does describe the multi-particle quantum mechanics of identical fermions. So this is a slide we used already a while ago, where you verified that this two-particle state created by acting field operators twice on the vacuum state, because one psi dagger creates a particle at position x1, another psi dagger creates a particle at position x2. And for the case of the normal bosonic the fields, psi dagger x1 and psi dagger x2 commute, namely that you don't need to be worried about the order of these two creation operators. And that property told us that the wave function that describes two-particle state is symmetric under the interchange of two particles. So what we did is to write down this general form of two-particle state, which you have seen already probably way too many times by now, and that was part of your homework problem. But because these two psi dagger operators commute, I can interchange the orders between them. So now, instead of writing down psi dagger of x1, psi dagger of x2, I can write it also as psi dagger of x2, psi dagger of x1 in the opposite order. It doesn't change. But in this expression for a general two-particle state, given together with this coefficient function capital of psi, x1, x2 are dummy variables for this integration. So I can freely relabel them. So I call x2 by x1 now, x1 by x2 now. So this psi dagger of x2, psi dagger of x1 is now written as psi dagger of x1, psi dagger of x2. But at the same time, I have to consistently interchange x1, x2 everywhere in this expression. This coefficient function capital psi depends on x1, x2. So now I have to interchange the arguments of x1, x2. So now this capital psi has this order of the arguments as x2 first and x1 next. And if you compare the first line and the last line, everything up to the vacuum state is now the same. The only difference is that this coefficient function capital psi now has two arguments interchanged. And it is supposed to be connected by equal signs all along. So what you learn is that capital psi is symmetric under the interchange of two particles. And that's how we learned that this quantum field theory construction really gives you a two-body quantum mechanics of identical bosons. And you can generalize this to arbitrary number of particles. Psi daggers commute no matter what the arguments are, no matter how many of them you have. And therefore, you always find this capital psi to be symmetric under interchange of these arguments. And therefore, they describe a wave function of a multi-particle system of identical bosons. So that's we managed to convince ourselves that QFT is really the same thing as multi-particle quantum mechanics. Of course, I emphasized over and over again, even though the content is identical, this framework is more powerful because you have the Hilbert space, which consists of different states with different number of particles. And to describe Bose-Einstein condensate, we needed this funny linear combination among them in the form of the coherent state. So this was possible only because we switched to quantum field theory instead of sticking to multi-particle quantum mechanics. So it's the same thing, but it's just better. So that's what we argued so far. So now what we would like to do is extend this argument to the case when these two psi daggers anti-commute, and to see if that really leads to the multi-particle quantum mechanics of identical fermions. So far, I just reviewed what we have seen before for bosons, and now we switch to fermions next. So let me pause here again to see if you have any questions about what we talked about some time ago by now. Everything okay? Okay, good. I see some people nodding. So, okay, now we study the case of fermions. Once you go to fermions, two psi daggers now anti-commute. So when you interchange the order of these two creation operators, psi daggers, now you need to be careful about it, and you have to put the minus sign over here because they anti-commute. And this carries over to the last line, because from the second line to third line, all I have done is to relabel the dummy variables of integrals. So this minus sign would carry over. So again, by comparing the first line and the third line, it just amounts to interchange of two arguments in this coefficient function capital psi. But when you interchange the order of these two arguments, you have a minus sign. So that means this coefficient function capital psi is anti-symmetric under the interchange of arguments. And you can see immediately that if you have n particle states, then I use this creation operator n times. But whenever you interchange two operators, two creation operators, you always get this minus sign, which translates to the interchange of arguments of this multi-body wave function. And if you interchange any of the pairs, two coordinates in this function, then you get a minus sign now. And therefore, this coefficient function is anti-symmetric under interchange of any pairs of arguments. And that's precisely what you got told in quantum mechanics class. That's how you're supposed to deal with the multi-particle wave function of fermions. And there, you have to impose it by hand so that the wave function is antisymmetric. Here, that comes out automatically. Quantum field theory knows whenever you deal with the multi-particle wave function, they are supposed to be totally antisymmetric under interchange of any pairs of the arguments for the case of the fermion. It's totally symmetric under interchange of any pair of arguments for bosons, which ultimately come from the fact that they are commuting operators. But you're supposed to have a totally antisymmetric function under interchange of any pairs of arguments for the case of fermions, which arise from this anti-commuting nature of these creation operators for the case of fermions. Now, everything is automatic. You don't need to impose anything. QFT from the beginning knows the state has to be either totally symmetric or totally antisymmetric. So that's the idea of this fermion quantum field theory. So now we have the Schrödinger field Lagrangian looks identical, but you now specify the field to be this weird, classically anti-commuting Grassmann odd numbers. And when you quantize it, you find this set of the canonical anti-commutation relations. And using those canonical anti-commutation relations, they look identical to this fermionic harmonic oscillator we just talked about at the beginning of the class today. And that anti-commuting nature would lead to the quantum mechanics, multi-particle quantum mechanics of identical fermions, where the wave function is anti-symmetric under interchange of any pairs of the arguments of the wave function. So that's the idea of dealing with fermions in quantum field theory. Okay, let me stop here again. I'm sure you have some questions about this.
Yeah,
Adi?
I have a question.
Go ahead.
So when you say QFT knows or it's built in, isn't this only because we had the foresight to set up an anti-commutation relation? Isn't that didn't we set that up for this purpose? Or
yeah,
like,
so
you know what I mean?
I think what you're saying is that my argument is circular, and that may be true. So we know this works. That's why how we actually use it. So one can ask the following question instead. Now that we have QFT, could there be a different ways the statistics would arise in QFT? For example, is there any other possibilities beyond fermions and bosons? It turns out there is. And there's something called anyons. And when you interchange the order of two particles, then you get a phase instead of a sign. And this can be done only in two-dimensional system. So if you have a plane, if particles live only on two-dimensional plane, you can define the orientation in interchanging two particles. Do you interchange particles anti-clockwise, or do you interchange particles clockwise? And if you have 3 dimensions, you can't tell them apart because you can rotate the whole plane, and then clockwise interchange becomes anti-clockwise interchange. So they are the same thing. There's no difference between them. But only in strictly two-dimensional system, you can define whether you have done the interchange clockwise or anti-clockwise. So 2 operations are now inverse operations to each other. In that case, you can assign a phase. When you have 2 fields, when you do clockwise rotation, you get a phase e to the I theta. So psi x1, psi x2 is equal to psi x2, psi x1 times e to the I theta. And theta equals 0 corresponds to bosons. Theta equals pi corresponds to fermions, because that's anti-commuting. But in principle, it could be anywhere in between. It could be any phase, hence anyon, any-on. And that, again, might sound like a totally bizarre, weird academic interest. It turns out that they do appear in fractional quantum Hall effects in condensed matter physics. Elementary excitations in the fractional quantum Hall state turns out to be an anyon, and they have these weird statistics, which is possible only in two-dimensional system, which the fractional quantum Hall state is. So in principle, you can have more general statistics once you have QFT. And I'm afraid I'm not actually going into that in this course, but I hope you can look it up. If you just Google FQAG, fractional quantum Hall effect, and anyon, I'm sure you'll find hits and you can read about it. So here we are talking about only commuting and anti-commuting numbers because these are the only cases we are going to discuss. But in general, there are wider possibility which you can formulate within a quantum field theory. Maybe, so that I hope would be partial, at least partial answer to question, Adi.
Thank you.
Okay, any other questions here? Chirag?
Yeah, just a clarification. So the fermion field operators commute with the boson field operators, right?
That's right, yep. So as I said before, even is a commutator. Even odd is also a commutator. Odd follows anti-commutator. So if you have a product of even operator and odd operator, you can interchange their order without any problems. But when you have the product of these 2 odd operators, 2 Grassmann odd operators, then when you interchange them, you need to put minus sign. So you have to be a lot more careful when you manipulate the algebra among these operators. Thanks for asking that question. Any other questions? Okay. So now we start putting the chemical potential, just like what we used to do in the case of bosons. So when you put chemical potential, you add this term mu psi dag of psi. And Hamiltonian is psi dag of psi dot minus L. So that cancels this first term. And so Hamiltonian has these two terms now. And as you have learned already, once you go to momentum space, the first term just becomes p squared over 2m. Second term is just number mu. So for each momentum mode, you have these creation annihilation operators, and with this sort of eigenvalue of the energy, p squared over 2m minus mu. And now we're talking about A being anti-commuting objects. So sorry, I switched the notation from B to A for a while when we try to really discriminate for bosons versus fermions. But I hope by now you've gotten used to this idea of anti-commuting creation annihilation operators. So I use this general notation of A instead. And now what we have learned before is that case with positive chemical potential didn't make sense because you can arbitrarily lower energy of the system because coefficient of A dagger A is negative if momentum is small enough. P squared of 2m minus mu is negative. Then you can put more and more particles into the system and you keep lowering the energy. So there was an instability. And that's the case you observe this animation and real data of this boson system collapsed. So there was no stable ground state in the system. So it didn't make sense for bosons. But even with the positive chemical potential, without repulsive interactions, which would have stabilized the boson condensate, even without the repulsive interaction, the positive chemical potential can still make sense in the case of fermions because you cannot put more particles into the system arbitrarily. You are stuck when you put one into them, and you cannot put any more into the system. So even for negative p squared over 2m minus mu, it still gives you a well-defined ground state in the case of fermions. So that's a big difference from the case of bosons. So in the case of bosons, as I said already, you can put arbitrary number of particles into the system. And when p squared of 2m minus mu is negative, then by putting more particles, you can lower the energy. And therefore, you can put more and more particles into the system and arbitrarily lower the energy of the system. So there's no grounds to say to the system, and hence boson over. But things would change when you talk about fermions. So that's something we'd like to talk about next. So this is the review of what we talked about in the case of boson condensate. But nonetheless, if you have any questions, please ask now before switching to fermion. It's okay.
There's a question.
Oh, Adi, go ahead.
I was just saying there's a question in the chat.
Oh, what is it lambda less than lambda? Okay, so the lambda was when lambda was the quadratic term in the Lagrangian. When lambda was positive, you put in the repulsive interaction, and repulsive interaction stabilized the system so that you had a BEC, and that's because this one corresponds to the negative quadratic term in the potential in the field space, and quadratic term will bring it up, and you find a well-defined the bottom of the potential. And so the positive lambda, namely repulsive interaction, would have made the BEC stable. In other words, unless you put in the quadratic potential, namely the repulsive interaction among particles, you could not find a stable ground state. So when you turn off the repulsive potential, then you find only this negative quadratic potential, which keeps down the hill, and therefore you don't find the stable ground state. If you make lambda positive, negative, that's even worse. It just keeps rolling down even more steeply, and again, you don't find a stable ground state, and hence you had a collapse and boson over. So lambda equals 0 doesn't have ground state. Lambda negative doesn't have ground state. Lambda positive would have a ground state, and that was a situation with the bosons and condensate. So I'm sorry that I used lambda without telling you that that was meant to be this quadratic term in the Lagrangian, because that's a symbol we used before. So I was relying on, what you might have remembered from this. But nonetheless, that was meant to be a possible quadratic term in this Lagrangian. And when lambda is 0, that's the case we are looking at here, or when lambda is negative, that's even worse, you didn't find the stable ground state. And that was what was meant when I introduced this lambda here in this bullet. Does that answer your question, Adi?
Yeah, thanks. Sorry, I just
Oh.
I think I was confusing lambdas and mu's.
Okay, sorry about that. Yeah, so that was Natalie. I'm sorry, I didn't read the name. Okay, thank you. I see. So that was a question from Natalie, and Adi reminded me that there was a question in the chat. So I appreciate that. Yeah, thank you. Otherwise, I would have missed it. Okay, any other questions? Okay, so now we look at the case of fermions, and even without repulsive potential, you do find a well-defined ground state with positive chemical potential. That's the major difference here. So in the case of fermion, ground state of this Hamiltonian is pretty obvious. You use the vacuum state for every momentum where p squared over 2m minus mu is positive, because if you put one particle in there, you would increase the energy. So that's not the ground state. So you keep the state vacant. So that's the idea for the momentum modes when p squared 2m minus mu is positive. But for the momentum modes where p squared 2m minus mu is negative, this whole thing in parentheses is negative. So if you put one particle into the system, then that would lower the energy. So you like to use the singly occupied state for the momentum modes where p squared 2m minus mu is negative instead. But unlike the case of the boson, you can't put more into the system. It stops there. So you cannot arbitrarily lower the energy beyond this. And therefore, this actually becomes the ground state. So idea is very simple. You occupy all the states up to the momentum, which is called the Fermi momentum, Pf, where Pf squared minus over 2m is exactly mu. So for all the momentum modes below Fermi momentum, because p squared of 2m minus mu is negative, you gain energy by putting a one particle into the system. So you occupy all of these momentum modes up to the Fermi momentum. But above the Fermi momentum, p squared over 2m minus mu is positive. So you lose energy by putting a particle into the system. So you rather not. So you keep the state unoccupied. So this is the ground state. Remember, this is the system of arbitrary number of particles, because we're talking about QFT. Your Hilbert space includes states with all possible number of particles in it. And in this huge Hilbert space, you're looking for the ground state with the positive chemical potential. And ground state is very simple. You occupy all the momentum modes up to Pf. You do not occupy all the momentum modes above Pf, and that's the ground state. So even when talking about low temperature and high density, and for the case of bosons, you had this very funny behavior of the bosons and condensate, where millions of particles start to behave like a classical wave. Case of the fermion is a lot simpler. You just occupy states up to a certain momentum. You do not occupy states above certain momentum. And this state is called Fermi Degeneracy or Fermi gas, or also called Fermi liquid, when you start to introduce interactions among them. And this is actually a very simple description, because even when you have some interactions among them with a characteristic energy of called delta, if delta is much smaller than the Fermi energy, namely Pf squared 2m, that perturbation of the system cannot move particles in here, because if the perturbation would start to move particle of one momentum to another particle with a different momentum, that state is already occupied. Namely, your perturbation doesn't do anything. Namely, this Fermi gas or Fermi liquid is so rigid any small perturbation would not change it because all the states up to PF are all totally occupied. You cannot change anything. The only change that can happen is only particles near the Fermi surface within the size of the perturbation delta. In those states, the particle may get excited over here, maybe de-excited down here. So those particles may move a little bit near the Fermi momentum, but the bulk of the system is very stable against any little perturbation to the system. So if you don't put any perturbation, if you don't put any interactions among particles, you talk about Fermi gas, because it's just a system of identical fermions with no interactions among them. But even if you do put interactions among particles, this state is pretty robust. Doesn't change much as long as the perturbation of the system is smaller compared to the Fermi energy, Pf squared over 2m. So then you call that system as a Fermi liquid, because you did take interactions into account, but nevertheless, system looks very much like this, up to possible perturbations near this Fermi momentum. So we talk about Fermi liquid. Even when we talk about interactions among particles, this ground state is very robust. So that's the idea of the multi-particle fermion system. And in fact, you have seen this kind of situation already in talking about atoms. You occupy various orbitals from the bottom up to the number of electrons you have in the system, and that's it. And you can talk about excited states to bring one occupied state to another unoccupied state. Then you're talking about the excited state of a given atom. So you have already secretly used this idea of the Fermi liquid when you talk about the electron, multi-electron atoms. And even if you include the Coulomb repulsion among electrons, implicitly you assumed that your description of putting electrons into individual orbitals still makes sense. Maybe your instructor didn't say it very explicitly, but you have actually secretly used this idea that interactions among fermions do not drastically change the picture of just occupying each state from the bottom to the number of particles. And that's the idea of Fermi liquid already. So idea is that for the case of the ground state of multi-fermion system, you just occupy states from the bottom up to the number of particles you have in the system. That's the Fermi gas. And if you include interactions among them, like Coulomb repulsions among the electrons in the multi-electron atom, your picture doesn't change much. And then you call that Fermi liquid. And somehow, magically, you have taken care of the repulsions among the electrons without drastically changing the state you were looking at. So that's the meaning of how robust this Fermi liquid idea is. So in condensed matter systems, not just even, say, 100 electrons in multi-electron atoms, you will be talking about Avogadro number of electrons, 6 times 10 to the 26 electrons. You can still apply this idea of Fermi liquid, and that's how we can get a pretty simple description of condensed matter physics, even though you are facing this huge, it looks like an unsurmountable problem of dealing with 6 times 10 to 23 multi-particle system. But using this idea of Fermi liquid, it actually turns out to be fairly simple. And so this is actually sort of conceptual point. I'm sure you got questions, so let me pause here and see you got questions about this. No? Sure? Well, of course, you'll see this idea of Fermi liquid in action as we move into various examples. So hopefully, if you are still a little bit so unsure about this whole idea, that will start to sink in. So bottom line here is that when you have fermion system with positive chemical potential, and if you instead talk about energy states instead of momentum states, like in the multi-electron atom, then you start occupying each state with 1 electron per state up to Fermi energy, if you use the energy space instead of momentum space. And that's what you have done with the multi-electron atoms already in quantum mechanics. So this is a generalization of it. And mu, therefore, has the meaning of Fermi energy. Namely, every state up to Fermi energy is supposed to be occupied. Above Fermi energy, you will keep the state unoccupied. And that's how you define the ground state of the system. And now we start to look into an explicit example of this away from multi-electron atom, which you're already familiar with, now applying to, for example, things like nuclear physics, which is also multi-electron system made of neutrons and protons, and condensed matter systems, where you have this huge number of electrons in a given system. So we start looking into these examples next. Okay. Any questions?
Professor, oh, go ahead.
Okay, go ahead, Adi.
No, someone else.
Natalie?
I think
Okay. Natalie?
Thanks. A technical question. It confuses me that we call states excited states once we act the accretion operator on them, even if they're the ground state. Like here, we're calling one a ground state if it has a certain chemical potential energy.
That's right.
So
that's why I'm using separate notations here, right? So in the case of bosons and condensate, I call the ground state GS. Zero state is what I refer to as the vacuum state. So zero state is a state with no particles in it. But there's no guarantee that the vacuum state is the ground state of the system. For BEC with positive chemical potential, then you had a coherent state rather as the ground state. So this is the same idea. If you have positive chemical potential, then vacuum state is not the ground state of the system. Instead, this Fermi liquid is the ground state of the system. I hope you see the analogy between the two cases.
Yeah.
Does that answer your question?
Yeah, it did.
Okay, good. And Adi?
Yeah, I was just wondering if this had anything to do with superconductivity when you say that the interactions are limited at very low temperatures. So
right, and we will come to that.
Okay.
Any other questions? Chirag?
I have a question not directly related to this slide, but I'm just thinking about just anti-symmetrization in general.
Okay.
I remember in 137b, we saw that that led to like an effective potential between fermions. So I was wondering if, like, how does that play into the formulation we have here?
So can you tell me what you meant by effective potential?
Like we saw that there was, like after anti-symmetrizing the wave function, there's like some sort of interaction term that comes about between the fermions.
Like what?
I think that was like even without considering like Coulomb repulsion or anything, we saw that there was anti-symmetrization led to some sort of repulsion, if I'm remembering correctly.
Yeah, so it's not repulsion, but when two arguments are the same positions, then wave function vanishes. So it sort of looks like fermions naturally repel each other because they cannot come to the same place. I think that's what you're referring to. So it is not a force of any kind. It's not an actual repulsive force because it's not part of the potential energy in Hamiltonian. But there is this requirement that when two particles come to the same position, then wave function vanishes. There's no probability for it. So fermions would like to stay away from each other. Bosons want to do the same thing together. And that's what we see in bosons and condensate. Fermions want to do different things. So if that guy's doing that, I'd rather doing something different. That's the idea of what I call diversity principle, right? So that's the tendency. So that kind of looks like people want to always socially distance from each other. The fermions don't like each other somehow. They want to stay away from each other. So that kind of looks like there is a repulsive interactions among them. It's not an interaction, but it's just a consequence of this anti-symmetrization of the wave function. Is that the kind of context you have in mind?
Yeah, I think so. I'll look into it a little more later.
Okay. So if you have some more specific definition of what you meant by effective potential, we can talk more about it. So please look it up. Yeah.
I
Adi?
think
Professor, I think he's talking about exchange forces is the term. Chirag, right? Exchange forces. That's the
Uh-huh.
effective potential
I
term.
see. I see.
Yeah. So is that what you were explaining? I'm not sure.
Yeah, exchange force is the idea that when you actually have particles spin one half, which is the case, of course, the electron, when spins are same, then they are not allowed to come to the same position. So when spins are the same direction, then they, in some sense, repel. But if the spins are opposite direction, they are allowed to come to the same position because they are different states. So depending on the relative orientation between spins, parallel spins look like they repel, and anti-parallel spins don't seem to have any forces among them. So that is the origin of the exchange force. And if you write as a Hamiltonian, you can write it as S1.S2 with a positive sign, so that when the spins are pointing the same direction, you get additional energy because of it. And that might look like a force. So that's the idea of the exchange force. Is that the context, Chirag?
Yeah, I think so. I just looked it up
Okay.
right now. I think the
right.
central idea is just that like the expectation value of the separation is higher, which makes sense given the Pauli exclusion principle.
Right, that's right. Okay, thank you, Adi, for the clarifying question. Anything else? Going back to the other slide. So for bosons, positive chemical potential without repulsive interaction didn't make sense. But for the case of fermions, even in the absence of interactions, the ground state is well defined for a positive chemical potential. That's the first statement. And now that we identify the ground state with no interactions among them, it turns out that even if you do include interactions, then this Fermi liquid state is very robust, because the fermions cannot change their state at all because they are all occupied, and this state overall gets modified very little, except for the momentum or energy modes close to what is called the Fermi surface, which is the edge of the states that are occupied. Apart from near the Fermi surface, the bulk of the states is not modified, not affected by smaller perturbations of the system, and that's why Fermi liquid idea is very useful. And Fermi energy, in this case, is just given by this free particle energy with a Fermi momentum. If you have more complicated system, like in semiconductor, then you have a different spectrum of energy as a function of momentum. So it's not purely p squared over 2m, but you can still apply the same idea using the energy axis rather than a momentum axis, and you occupy all states up to Fermi energy, which is given by the chemical potential, and you keep all the states unoccupied or vacant for all the states above the Fermi energy. So that's a general concept of the Fermi liquid. Okay. So now we apply this idea with a simple approximation that you can treat this really as if they are free particles with the energy p squared over 2m, which is an idealization. But it turns out that that's a pretty good idealization approximation in the case of metals. And you might have seen this in a class in condensed matter physics if you're taking one. And let me put this system into a box with the periodic boundary conditions. So as we talked about before, if the system is in a finite box with the periodic boundary conditions, your momentum modes are quantized in the unit of 2 pi h bar over L. L is the side of this box with the integer quantum numbers. Then you know how to count the states. Then you can actually come up with the number of particles in the system up to Fermi energy. And that actually turns out to be this quantity, namely that the Fermi energy is given by mu, the Fermi momentum is given by 2m mu square root. So this is the Fermi momentum. And up to Fermi momentum, you count the number of states by assuming that this is a sphere. So 4 pi over 3 times Fermi momentum cube in the unit given by 2 pi h bar over L. So this is the total number of particles you have in the system. And I'm still ignoring spin. So to the extent I ignore spin, this is the total number of electrons you have. up to the Fermi energy mu. Then number density N over V is given by this quantity, just dividing this by the volume of L cube. And in the metal, you basically have maybe 1 electron per ion at a given site of the lattice. Maybe you have a few, depending on what kind of atoms you have in your system. But overall, you expect to see 1 electron per a few angstroms. So typical separation between the lattice sites, that's the lattice constant. So if you actually demand that this N over V, number density of electrons, is 1 per a few angstrom cube, then you can estimate what the chemical potential should be, knowing the mass of the electron. So you can work out mu, and mu has a dimension of energy. And if you divide by the Boltzmann constant, you can convert it to the dimension of the temperature. So that turns out to be about 10,000 Kelvin. So typical energy scale involved in this Fermi liquid for a metal corresponds to the temperature of 10 to the 4th Kelvin. Namely, the room temperature of the order of 100 Kelvin is very cold from the point of view of electrons in the metal. Because the room temperature is so cold, this energy at the Fermi surface is so high compared to room temperature, then the ground state is all you get. You can totally ignore the thermal excitation of electrons near Fermi surface to go up to unoccupied state, because that's extremely Boltzmann suppressed by e to the minus 100. That's an extremely small number. So ground state is all you care about to describe metal, all the electrons in a metal. And that's how you can talk about how metals would conduct. You can compute its conductivity, you can compute the number density, you can compute all kinds of properties, you can compute the pressure, as if the metal is just a gas of non-interacting electrons occupying all states up to the Fermi energy. And that's actually already a very good approximation in describing a metal. And that is something you can do because you're using this language quantum field theory, talking about unoccupied state, occupied state in this huge Fock space. If you want to deal with a piece of metal by writing down the wave function with 6 times 10 to the 23 arguments in it, that's a hopeless problem. But using this idea of QFT, you have this very simple description of it. You just say 1 all the way up to Fermi energy and say 0 all the way above Fermi energy, and that's it. That's your state. You don't need to write wave function with 6 times 10 to the 23 arguments in it. Just by showing this, the schematic graph, you know exactly what you're talking about in the spirit of quantum field theory in this huge Fock space. You know what ground state you have in your mind. And then you can start computing things with this ground state. And that's how you can describe all the electrons in a piece of metal. And thanks to the fact that room temperature is so much lower compared to the typical excitation energies of the metal, then you can only talk about ground state. You don't need to talk about anything else. And that's already a good description of the electrons in metal. So that's the first application, simplest application we can do with this idea of the Fermi liquid. Okay, any questions about this? And you may well have seen this idea somewhere else. Chirag?
So does this mean that, yes, it does mean that, I mean, since you have 1 electron per momentum value, isn't that sort of fixing the number of electrons that you can have in the metal?
Yeah, that's right. So for a given chemical potential, which is the Fermi energy, you can predict how many number of electrons you can have in the system because you occupy every state up to that energy. So the number of electrons you can have in a system just corresponds to how many states there are in your system. And if you can take the continuous approximation, you talk about the density of states. So you integrate density of states up to Fermi energy, and that's the number of electrons you can have in the system. Or in
So
other
when you
words,
say
when you have a system with a fixed number of electrons, you can walk backwards to identify what the Fermi energy should be for that system. So they are in one-to-one correspondence. Sorry, you want to speak. Sorry, I interrupted you, Chirag.
Yeah, I was just, I guess I was just, so is this referring to the free electrons or just like the bound states too?
So here I'm talking about free electrons because that's already a pretty good approximation for simple systems. When you have more complicated things like the solid, the semiconductors, you talk about bands. So energy of a single electron is no longer p squared 2m, but more complicated function of the momentum. But you can still apply the same idea of just keep occupying every state up to certain energy. And then that's the Fermi liquid. So then it's not longer free electrons in the sense that it is subject to more complicated interaction with the lattice of ions. That's why it's not p squared 2m anymore. So you have included the effect of interactions with the lattice that way. But same idea would apply, and you can still talk about this Fermi liquid.
Essentially, the chemical potential is dictating how many electrons can escape the bound states.
Right,
sort of.
Right, exactly.
Okay, sure. Thanks.
Any other questions? All right, and the same idea can also work in stars. And if you have a star like our sun, and it's burning and emitting light because of the nuclear fusion process happening in its core, and it's mostly hydrogen fuel. At one point, even our sun would run out of this fuel in about 5 billion years from now. So you have to come up with an escape plan before then. And then the sun would blow up into what is called the red giants. Our planet Earth gets swallowed by expanding surface of the sun. And eventually the sun would even further lose energy, and then eventually it becomes what is called the white dwarfs. No nuclear fusion process is happening anymore. It doesn't produce any energy anymore. But somehow it manages to sustain it, somehow managed to keep its finite size without the gravitational collapse, because there's some pressure in the system without producing any energy. So the question is, where does the pressure come from? The pressure in this case comes from this Fermi degenerate liquid of electrons. So because once you occupy electrons all the way up to a certain Fermi energy mu given by chemical potential, if you want to squeeze a system into smaller volume, then you have to bring some of the electrons to a higher energy levels because you have less number of momentum states with a smaller volume. We have seen that on the previous slide in the case of metal. So making volume smaller would increase the energy, which means there's a resistance to make the system smaller, which is nothing but the pressure. So this is what is called the Fermi degenerate pressure of the Fermi degenerate electron gas or liquid. So just having to do with this Fermi statistics gives you a finite pressure, unlike bosons, which can go all the way to collapse and lead to boson over. The fermion system has a pressure of its own, just being fermion. And it turns out that the whole star can be sustained because of the Fermi degenerate pressure. And if you do the math, then you can actually work it out. Once nuclear fusion stops, no heat and no thermal pressure generated, but just being this Fermi degenerate gas that already comes with the degeneracy pressure, so-called. So that can sustain its finite density, and that can lead to hydrostatic equilibrium. And if you actually go to the real number of electrons you might have in an entire star, which is of course a huge number, even much beyond Avogadro number, you need to have a pretty high Fermi momentum to sustain that mass. And it basically becomes totally relativistic. So it turns out that you can treat this entire star as a gas of relativistic electrons, where you can ignore the mass of the electron now, and energy is given by just speed times the momentum. But you know still how to count the momentum states in a given volume. So you can count them up. For each momentum, energy of the electron is c times momentum. And if you fully occupy all the electrons up to Fermi momentum with this relativistic limit, you can sustain only a finite amount of mass that way. So there's some limit to the mass, how much you can support using Fermi degenerate gas. And that maximal mass is what is called the Chandrasekhar limit. And if you look at my lecture notes on fermions, I work out this hydrostatic equilibrium and come up with a fairly precise estimate of this Chandrasekhar limit. But instead of talking about this real calculation, what you notice here is that the mass of the star comparable to mass of a sun. So this is m(o) dot is actually the mass of the sun. That's a notation. Is given by fundamental constants like h bar because it's quantum mechanics, c because of relativity, g Newton's constant because the pressure has to compete with the gravity, and the mass of the proton or neutron. Using these fundamental constants, you can get the mass of the sun. So the mass of the sun is determined by these fundamental constants, and which is really amazing. The star is something you can compute with these fundamental constants using the idea of this Fermi degenerate C. And that kind of star is called white dwarfs. They're dwarfs because they're actually very small, much smaller than the size of the sun. So, but once it becomes small enough, this Fermi degenerate pressure can sustain the whole mass of the whole star. And that is limited by this maximal mass called the Chandrasekhar limit. So that's the idea, how this idea of Fermi degenerate gas can be applied very universally, even across the universe, by talking about this mass limit. And Chandrasekhar is the physicist originated from India, and he got Nobel Prize for realizing that there is a maximum mass the Fermi degenerate gas of electron can sustain in support. And so without doing this very complicated calculations, I'd like to show you just a back of envelope estimate of this. So gravity of a system of mass m in size r gives you potential energy, self-energy of Gn m squared over r. And in the case of the Fermi degenerate gas of electrons, you have Ne electrons in it, but each electron should be accompanied by a proton to neutralize the electric charge. And proton is much heavier than the electron, so the mass of the star is basically given by the mass of the proton times the number of electrons. And for a given number of electrons, you work backwards what the Fermi momentum is for a given size r. Then you know how much energy there is by occupying electron, each is now relativistic, so energy Cp up to the Fermi momentum. So this is the energy of the system. And you basically assume that this is the energy from Fermi degenerate gas that gives you the pressure to resist the gravitational attraction that wants to collapse the star to a point. So this energy from the Fermi degenerate gas should basically balance the self-energy from the gravity. So this is just an order of magnitude estimate. So they must be comparable to each other. And that already gives you this estimate that the mass has to be bounded by this combination and with some order 1 constants, which we did not compute. This is just order of magnitude estimate. But now you estimate the size of the mass of the star using these fundamental constants, which is a big number, but that's indeed comparable to mass of the sun. So this idea of Fermi degenerate gas works in the universe, and you can work out the mass of a star using these fundamental constants, knowing this idea of the Fermi liquid. So that's what I wanted to tell you. So I stop here. I already is over time. Are there any questions?
Are you assuming that star is mostly hydrogen when you do this like mass approximation because you're not ignoring all the other atoms and neutrons?
Good question. So here I ignored neutrons. But if you have mostly oxygen, carbon, silicon, that's what the typical white dwarf is actually made of, then you typically have 2 nucleons, 1 proton and 1 neutron for each electron. So I have to multiply this by a factor of 2. That's why on the previous slide, I have this expression of Z over A. Sorry, this animation takes some time. But and if you do a complete calculations, you have to know what is the typical composition in terms of how many neutrons you have for a given number of electron. So you have this ratio of 2Z over A because of that. So what I'm doing in this back of envelope estimate is just the order of magnitude estimate. So I'm ignoring the factor of roughly 2 when you compare the mass of the star to the number of electrons. But even then, you still get a pretty good estimate of the mass of the star that way. Okay, any other questions? Thank you for clarifying question, Adi. Everything okay? So I'm basically giving you various examples with a simple idea of occupying all the momentum states, even assuming that they are free up to a certain Fermi momentum, works very well in describing like piece of metal and even entire star where you have to deal with huge number of electrons that seems to be completely beyond your control in the standard quantum mechanical wave function. But using the idea of QFT, you have very simple description of those systems, and you can be even successful quantitatively that way. And so that's why I'm showing these examples right now. Okay. Any further questions? All right, so I see you on Friday.
Thank you. Thank you.
Thank you.